Imagine your computer had absolutely no way to organize its memory. A hard drive stripped of its underlying logic is simply a massive, unorganized expanse of raw digital static. Without folders or file names, finding a single saved document would mean forcing your computer to physically read every single byte on the drive, straight from the beginning to the end, just to locate one piece of text. The only reason your system functions is because of an invisible architectural layer sitting between you and that raw data, known as a file system. This diagram shows how the system imposes order. By organizing scattered data into a clean, hierarchical tree, the computer can instantly retrieve specific data points from the chaotic void in milliseconds. While we often measure a computer's speed by its processing power, that processor relies entirely on the file system's underlying ability to impose structural order on the digital chaos. Let's look at the exact fraction of a second when you hit Save on a new document. Your operating system doesn't drop that information onto the disk randomly. It immediately hands the raw data off to the file system to begin a highly specific structural mapping process. The file system assigns 4 properties to raw data: a readable name, physical disk location, exact file size, and security permissions. Because these tags are permanently attached, the file is instantly recalled without searching the whole drive. Different computing environments, like a personal laptop versus a global server, have drastically different priorities for how these properties are handled. Therefore, they require entirely different architectural engines to run them. Think about a standard local personal computing setup, like the Windows PC sitting on your desk. Microsoft relies on a file system called NTFS. If you look at your C drive right now, NTFS is the engine running it. The architectural priority of NTFS is safety and local control. It is designed specifically to handle complex user security permissions and manage massive pools of local storage safely. If we move away from local desktops to the massive scale of enterprise server racks and cloud infrastructure, the requirements change entirely. Here, EXT4 is the architectural engine of choice. It powers Linux environments, acting as the foundation for enterprise tools like Docker, JBoss, and Tomcat. Docker is a platform for building and packaging software into isolated containers, while JBoss and Tomcat are server applications used to host complex web environments. EXT4 operates on a different design philosophy. It sacrifices some of the complex local security features found in Windows in order to prioritize raw speed, absolute reliability, and the handling of massive, continuous file transfers. This comparison table maps out the general rule. NTFS acts as the security fortress optimized for Windows, while EXT4 serves as the high-speed engine optimized for Linux. Choosing the right operating system inherently means choosing the correct data management engine for the specific operational task at hand. Zooming out to the macro level, the file system operates as the absolute bedrock of overall system stability. When you encounter common technical failures like sudden disk errors, storage crashes, or severe speed bottlenecks, they are frequently tied directly to the file system architecture rather than physical hardware degradation. Mastering this structural layer is a non-negotiable requirement for any professional entering DevOps, cloud architecture, or system administration. You can diagnose a machine's current file system architecture yourself by opening a terminal and typing the command df-th. The output will immediately reveal exactly which system is actively running your machine. To continue mastering these invisible systems and build real-world IT knowledge, subscribe to ADILinux and drop a comment below with the word file system. In our next video, we will tackle the next critical concept required to fully understand how data is tracked: the inode. An inode is a data structure on a Unix-style file system that stores the administrative metadata about a file, completely separate from the file's name or actual content. Understanding the architecture of order is the essential first step to mastering the machines that run the modern world.